So hopefully I didn't overwhelm you when we were talking about friction. Um, like I said, I'm not going to do a huge amount of friction for you because I know it's not something you're going to sit down and calculate. Will you apply the principles? 100%. You're always going to apply the principles that are associated with friction. Okay. Anytime you use a lubricant, whether you realize it or not, whatever scenario it's happening in, you're reducing friction. It's extremely important in trades. I was listening to a video that I was giving the automotive group about reducing friction in NASCAR races. And they actually manufacture some of the parts to have silicone embedded in the metal to reduce friction. I thought that was interesting. I know a lot of my machines that I use are lubricated with graphite. And one of the nice things about lubricating with graphite is it doesn't have to be changed as often. It's not like oil that dries out. Graphite has some really cool chemical properties that make it excellent for being an inert lubricant. So that's something that I found with some of my things. But I know whenever I have one of my sewing machines that starts acting up, the first thing I do is I check to see is anywhere's dry? Is there anywhere that we need to reduce friction? Is there any buildup anywhere? And it's surprising how much I've learned just from pulling them apart, doing my own maintenance and repairs, because there's not really much here for help in that regard, whether it's mechanical or electrical components that are in them. But I enjoy tinkering with that. So in this lesson, we're going to look at forces that include tension on ropes. So we're going to move slightly toward rigging because I know you do have a component where you deal with that. Now, if you're like the students that I've had other years, you will probably tell me, but somebody else calculates this stuff. I know. But it is a component of your trade, and it's a component that does show up when you're thinking about safety. And if you understand how it works, when you're on a job site and you're looking at what's happening, it can help you ensure that you are remaining safe and that any of your staff or your coworkers are also remaining safe. So we're going to look at just the force principles that relate to safety and how objects are suspended or hung. If an object is at rest, we say it's in static equilibrium. So static just means no motion, equilibrium, equally balanced forces. And all the forces on the object are balanced. So F net equals 0. This is an example of Newton's first law. I used to always have to look up the law numbers. I don't have to do that anymore. It's not one of those things that really matters, whether you know whether it's his first, second, or third law, but you should know what the three principles happen to be. And one of the principles is if all the forces are balanced and objects not moving, the net force is 0. So we're looking at a diagram that looks like this. So we are going to be looking at an object that's hung from a rope or a cable. Could be a piece of metal strapping. That would be another really good example. So you're hanging an object. This W is actually the force of gravity. So the force of gravity or weight pulls downward on the object. Whatever is being used to suspend it, whether it's the cable or a piece of strapping or anything, it is pulling upwards. That means there is what we call tension in the rope, and we use T to denote that. In order to find the tension, if an object is at rest, we know these two forces are balanced. So the tension is equal to the force of gravity. Now we're going to look at some scenarios where that is exactly true. We're going to look at some scenarios where we're not necessarily just using one rope to support it. We're using more than one to support it. And we'll look at, okay, if it's balanced, what does that tell us about the tension? Because that will tell us what we have to be concerned about if we're looking at ratings of cables. If you're lifting something heavy and you want to know, do I have a rope or whatever that will support it, you need to know how do the forces work. You might not sit down and do a long physics calculation, but you do need to know how the forces work. I'm going to get rid of my video because of where I have all my notes. And we're going to do some examples to explain what's happening. So this first example says, if an object with a mass of 375 pounds is supported by two vertical cables, what will the tension be in each cable? So I've drawn a diagram for you. The first thing we'll do is I'm going to label the diagram. And we're assuming the weight is equally distributed here so that the weight on each of these cables or it's going to be supported equally. Okay. Oops, I just wrote kgs. Anybody notice that the question is not in kilograms? It's one of the key things I did in this section. There's a couple times I've done it on purpose, not by mistake. We have 375 pounds. How many pounds are in a kilogram? There's 2.2 pounds in a kilogram. So we're going to divide by 2.2 in order to get kgs. And that's kind of the first section question to do here. So we have 170 kilograms. Now we need to think about the forces on this object. Well, we know this object, if it's suspended, if it's lifted, it will have a downward force caused by gravity. And gravity will pull down with a force that is equal to 170 kg times 9.81 meters per second squared. And then we'll calculate that, and that's equal to 1,668 newtons. Okay, so that's the downward pull of gravity. Now I know there's tension in each of these cables. And if they're equally positioned, the tensions are equal. So we can just use T to describe them. The upward pull in this cable, since they're equal, we know that the upward pull, which is 2 times tension, has to be equal to the force of gravity. Why? They're balanced. There's no motion, or it's in equilibrium. I got too many L's in there, too many U's, too many. We'll let it slide this time, but don't judge me. I've been writing this stuff for hours today. It's approximately 20 to 9, and I started recording things at 8:30 this morning, so don't judge me too harshly. All right, so now that we know this, let's substitute some information in. So 2 times the tension, so tension 1 plus tension 2, equals the force of gravity, which is 1668 newtons, dividing by 2. The tension is equal to 834 newtons. Well, why does this matter to us? Well, if I have a heavy object that I have to lift, and I know the rope or the cable that I'm using isn't strong enough to support it using one pull, one strand, I can use 2. I can distribute that weight and I can split it out equally. If we have 3 cables, we divide the weight in 3, assuming they are equally spaced. We're not going to deal with the fact of what happens if they're not equally spaced. That would require us to spend a lot more time working through these sections, time that there's really not enough room for by the time we have to get trig, electrical, and all the other little components that come into your course. All right. So pretty straightforward. Now this question said we're thinking about equal support. This is as complicated as we're going to get. Now this reminds us of trig, which I also think is good for you because it gets you thinking about trig questions. Now this question, I'm going to apologize in advance. I'm not sure I've left really enough space to do the work, so we'll try to do it so that you can follow it. Please, if you're having trouble following it, let me know and I'll do a further explanation. So in this example, we have an object that's suspended from a ceiling or a surface. And we want to know which mass is the heaviest. And then we want to know what's the tension in the string being pulled by the hand in the 2 final scenarios. So the first thing I'm going to do is we'll go through and figure out which mass is the heaviest, and then we'll go back and we'll find out the tension for the hand. Now the first one is pretty easy. This object is in equilibrium. If it's in equilibrium and there's 50 newtons of tension in the cable, we know that the force of gravity must be 50 newtons. If I want to know the mass, force of gravity is equal to mass times acceleration. So 50 equals mass times 9.81 meters per second squared. Rearranging it. we get a mass that is equal to 5.1 kgs. So that's for our first example. I'm boxing it off so that we can sprawl a little with our other calculation. And I'm going to section this one off too, because I need to make sure I stay organized. All right, now that we have that, let's do the second example. And maybe what I'll do is I'll change the pen color to help you out with the second example. So I'll throw a blue pen here. Hopefully color blindness doesn't cause any troubles. My husband's colorblind, so I often think of it. All right, now let's look at this case. How would we figure out the mass of the block here? Well, you'll notice the tension is pulling upwards, but it's pulling up on an angle. And gravity pulls straight down. How do I figure out gravity? Well, it's pretty easy. We've done this before. We did this in our last lesson. We make a triangle. We use trigonometry. I want to know what is the, I'm going to call it tension up instead of force. Let's go back. So I want to know the tension upward. Okay, so in order to figure out that, well, this side is my adjacent side. So we can use our trig. So that means adjacent goes with cosine, SOHCAHTOA. If you need it, write it down. So that's going to use that. So the cosine of 30 equals, this is my hypotenuse, the 50. So the tension up, oops, divided by 50. Rearranging it, we get 50 times cos 30 equals tension up, which is equal to, and we'll have to do the other one somewhere else, 43.3 newtons. Okay, so that's that tension. That's the upwards tension. That is the tension that is balancing gravity. 43.3 newtons. Okay. So if I want to know the mass, I think you can calculate it. 43.3 is equal to, sorry, I'm losing my train of thought. My brain is turning into sleep. And the mass of this object happens to be 43.3 divided by 9.81 gives us 4.4 kg. Okay. So it's not, if 50 newtons is still the tension in the rope, it's not quite as heavy. Well, what about if it's only 50 newtons of tension and we increase the angle even more? What happens to, what's the weight of the object going to be? Well, let's find out. So we'll do our triangle again. It's going to be exactly the same math as we have here. So it's going to be the cosine of 60 is equal to the tension up divided by 50. So you're going to have 50 times cos 60 equals, and you will get 25 newtons. Okay. So there's 25 newtons of force pulling upwards from this cable. So that means gravity is balanced by it, which is 25 newtons. Well, what's the mass? Mass is equal to, sorry, it takes me a few minutes to rearrange. And if I'm getting sleepy, I can't talk and rearrange at the same time. We get 2.5 kgs. I was going to change pen colors and I forgot. Okay, one interesting thing to notice, okay, when there is no angle, the tension equals gravity. When there's an angle, as the angle increases, the tension stayed the same, but it supported less and less of the weight of gravity. We're going to see that that's going to come into play when we think about if we're rigging something or lifting something. There's certain angles that we like to avoid. We don't like shallow angles because you'll notice here, 50 newtons of tension only is supporting 2.5 kgs of weight, whereas if we have 30 degrees and 50 newtons, we can support a lot more weight with the same amount of tension or the same amount of pull. So which mass is the heaviest? The first one, M1. What's the tension being in the hand? So I want to come back and I'm going to switch my color and I'll switch it to green to match the hand. So I want to think about, well, what is this force here in both of these examples? And it's going to be straightforward to calculate. So what's the force by the hand? Well, if the hand is pulling out, we notice tension is pulling in the other direction. And if it's balanced, they have to be equal and opposite. So if we can find out the tension that's being pulled back by the cable, we know what the tension is and we know what the tension is in the rope that's being pulled by the hand. So it's simple trigonometry, really. This side is my opposite side. So instead of using cosine, we're going to use sine. So we'll have the sine of 30 is equal to, I'm going to say it's the tension right divided by 50. Okay. And I'm going to leave it to you to rearrange. I know you know how to do that. The tension that is right happens to be equal to 25 newtons, which equals tension in the hand, because they balance. Now for the next one over here, we do exactly the same thing. Force in the hand. What do you think? Will it be larger or smaller? You know, if you're pulling something further and further, you can feel it's more pull in your hand. So we should have a bigger tension in the hand. So we're going to have sine of 60 equals the tension that's left divided by 50. And we're going to find the tension towards the left is equal to 43.3 newtons, which is equal to the tension in hand. So that gives us some examples with using some angles, and it also helps to see how angles can how the strength of a cable and the angle it's at can impact the mass it can support. So the smaller the angle that's up at the top, if we're thinking about, I'll put my video here so I can use my hands. But if you're thinking about creating a sling where you have two cables coming up to a point, the smaller this sling is, the more mass you can support, the more weight you can support. Whereas the wider the sling is, the less weight you can support. You put a lot of tension in the cable with very little lifting, actual lift power. Okay, so I'm maybe using the word power wrong there, over analyzing things here, but so that's what we're looking at. We're thinking about how do these angles impact, and we're going to look at that in a few questions. This is a similar type question. Again, we're just going to think about balancing forces in order to figure out tension. We are going to use another trig piece. And the trig is not overly complicated, but by the time you've done a couple of these, it should kind of make sense to you. So if the force, I'm going to go back to my red pen because it's my favorite one. Hopefully you don't mind. If the forces on this 35 kg mass, I must label that. I got to keep things where I can see them. Are in equilibrium, so everything's balanced. Okay, so we've got a note for that. And the angle is 40 degrees. Okay, what is the tension in each cable? Yikes, how do we figure that out? Well, let's just start with what we know. What's the one thing we could calculate even if we don't know a thing about cables? Well, we can figure out the force of gravity. So we'll start there. The force of gravity. is 35 times 9.81, which is equal to 343 newtons. Now that we have that, what balances out the force of gravity? Well, one of these cables is pulling upwards. Which one? Well, it's tension 1. So it's pulling up. Part of it is pulling up. Part of the force that's in that cable is pulling up. And the amount of upward pull it gives must be equal to gravity because all of them balance. So this is 343 newtons. Okay. So now that we have that, how do we figure things out? Well, let's think about trig. This is my hypotenuse. This is my opposite side. So to find T1, use trig. So let's figure it out. So we're going to have opposite goes with opposite goes with sine. So the sine of 40 degrees is equal to the force in the opposite side, which is 343 newtons, divided by the tension in cable 1. Let's rearrange. The tension in cable 1 is going to be 343 divided by the sine of 40, which happens to give us 533 newtons. We just answered one part. All right. How about tension 2? Well, for tension 2, it pulls horizontal, but what is it balancing? Tension 2 pulls in this direction, while there is a component, part of tension 1, is pulling in that direction. It's easier to draw it up here, perhaps. Okay, so part of tension 1 is pulling left. I get lefts and right mixed up, but I think I got it right that time. I think left is right. Okay, so how big is the pull towards the left from tension 1? Because that's going to be equal to the pull in tension 2. So let's figure out what tension 1 left is. How do we figure that out? Well, let's think about our trig. This side is adjacent to the angle. We know what the tension 1 is. We know what this is. So there's a couple ways we could calculate it. You could even use Pythagorean theorem if you really wanted to. I'm going to use sine and cosine because that's what I did when I wrote my solution. So what I said was, I know the adjacent, I know tension 1, so I can figure that out using cosine. So the cosine of 40 is equal to the adjacent side. That's what I want to find. So I'm going to call that tension 1 left divided by the size of tension 1, which is the hypotenuse, so 533. Tension 1 left is equal to 533 times the cos of 40, which is equal to, I wrote it down. I did write it down, I swear, 408 newtons, which is also equal to the tension in 2. And that's because they balance. So really just balancing all of the forces. A little bit of work, but it's not too bad. And actually the trig is not even terrible. You could say exactly the same math would apply if we took this block and we were using it, strapping around it. You would have more force on the piece that's the diagonal than you would on the horizontal component. That's pretty well always going to be the case. All right, I've got one more math example and then just a couple discussion questions and we're finished. So if the math is feeling a little overwhelming right now, we're almost done. And if you need more time on this, it's going to be a couple days before I have your next question done. So let me know and I'll adjust the release schedule and maybe give an extra review section on this. But because it's open book, you can look back through notes and that can help you while you're answering questions. So for this example, we have an object with a mass of 120 pounds. Watch that, pounds we're going to have to convert. What's the tension in each of the cables if it's suspended with equal angles measuring 25 degrees? So this is more like your classic doing a rigging lift. So you've got equal angles. If you have equal angles, we're going to have equal tension. We need to find the force of gravity. Well, we know its mass equals 120 pounds, which divided by 2.2 leaves us with 54.5 kgs. So the force of gravity will be 54.5 times 9.81, which gives us 535 newtons. Okay, now that we have that, let's think. If gravity is pulling downwards with that force, where are the upwards forces that are balancing it? Well, you have two cables. So oops. Let's see if I can draw a straight line. Let's just give that a re-go. Sorry. I'm going to draw them slowly just beside each other. So this cable pulls upward and this cable pulls upward. So both of them are pulling up. They each are going to support half of the force of gravity. So the force of gravity divided by 2 is going to be 535 divided by 2, which leaves us with a force of 267.5 newtons. So the upwards force on this cable is 267.5, and the upwards force on this cable is 267.5. And I think at this point, you know exactly what you need to do in order to find the tension. The tension is just going to be equal to using our trig relationship. So we have opposite side and we want to know the hypotenuse. So we're going to use sine. So the sine of 25 is equal to 267.5 divided by the tension. Tension is equal to 267.5 divided by the sine of 25, which happens to be equal to 633 newtons. The tension is always going to be a little bit bigger than the amount of gravity that it supports. And typically what they want to do is the tension in the rope here or in the cable, they want to keep it equal to or less than the force of gravity. So this would actually not be a particularly good angle. They'd usually like to keep that angle larger because it's going to put less tension in the ropes. And if we have less tension, that means we have less chance of breakage. So, kind of what I said. If the sling angle for lifting a heavy object, so the sling angle is just the angle that we're using to lift. So we've just flipped the picture from the last question. If the sling angle for lifting a heavy object decreases, what would be some issues that would cause concern? A sling angle of 60 is ideal. How would physics justify this? To answer this question, we're actually going to look at the next slide. So in this slide, and I'll do a little sketch. So in this slide, what we're comparing is this angle. So angle from horizontal. Now let's look at what happens. As the angle gets smaller, look at this, and this tension factor is how much the weight of the object is multiplied by in order to give us the tension in the cable. So you'll notice the tension is double the weight it supports if the angle is 30 degrees. Okay? If the angle is 60 degrees, the tension is very close to equal to the weight that the cable is supporting. That's right here. There's our 60. So what we usually want to do is these are the best angles because this is the very best one because it just works nicely for setting up for a triangle. 90 degrees clearly isn't going to give you a triangle, but these are the best angles because there is the least tension in cables. Let's say there's a cable that's had a little bit of wear and you're not aware of it. If you lift it using a configuration, so using large angles, sorry, I said large angles, using small angles. So, you're just barely wrapping the object. This angle here is really small, and then you're lifting it. You're putting extra stress on the cable, which could lead to failure. Depending on what you're lifting, that could be catastrophic. That could be very expensive. If you think about the cost of some of the units that you would install, I think a $5,000 heat pump is expensive. Well, maybe $4,000, $4,500, I think is what they each cost. I've got a couple of them in our house. And yes, that's expensive. But I know that's not expensive compared to lots of commercial applications or other pieces of equipment that you might be lifting and installing on a roof. You want to make sure that they're being lifted, they're secure, so that you're not responsible if damage occurs. So that's one of the things. We'll look back here. You like to keep your angles. 60 is the best. As the angle decreases, there's more and more tension in the cable because it supports a smaller and smaller amount of the weight of the object. All right, final question. This is another think and apply question. If an object goes from resting on the ground to moving upward as a crane lifts it, how will the tension in the in the cable supporting the object be affected during the initial few seconds as it accelerates? So usually with a crane, you want to lift at a constant velocity. That means the forces are balanced, but when it just starts to move, it speeds up. So we know gravity is pulling down. There's going to be tension upward. It doesn't matter what configuration we have. If it's accelerating up, what do you know about the tension? Tension has to be bigger than the force of gravity. So there's going to be more tension in the cable than you would normally have, which means that's the time when it's most likely to break or have failure. So those are the scenarios where you have to make sure or watch for failure and be extra cautious with during the first few seconds when something's lifted. It's one of the reasons why when you start to lift an object, you start slowly. You want to move into that lift as slowly as possible so that you reduce any tension on the cables, especially if it's a very large, heavy object. So hopefully that gives you a little bit of background on how to calculate tension and where tension is useful in your trade.